where he was the sole master's student to receive the Outstanding Research Award. Also, a recipient of the Graduate Research Fellowship. His work spans medical image analysis, visual language models, and document classification. He has published several journal papers, including IEEE and ACM transactions. Also, he has published papers in top tier conferences such as IJCNN and EMNLP. So, with this brief introduction, I would welcome Mr. Amol Joshi uh, in this session. So, Mr. Amol, over to you.
Uh, Hi, and thank you so much for the warm introduction. Uh, I hope I'm audible. Can someone please confirm that?
Yes, you are.
Okay, okay, thank you, sir. Just share my screen. Just a second, give me a couple of minutes. There's been some issue on mine. Just a
Okay, sure.
So any problem, Amok? Any problem you're facing or what?
yeah, because I'm kind of new to Teams. My presentation is just opening in presenter mode, and I think
Could you able to see the share button there? I mean, there is a share button. You have already, I think, shared your screen or what? I think
yeah, so I can share my screen, but it is being shared in the presenter mode. So I think even the notes are visible.
Okay.
Uh,
Actually, in the meanwhile, it was visible. Previously, it was visible.
but was it visible in the notes or just the presentation?
It was just like you were navigating.
Just make it full screen. I think that will not be visible.
Okay, let me just quickly try on screen.
Yes, now it is visible. It is visible. Yes.
Yeah.
Okay. Thank you so much. Okay. Sorry for the minor hiccup, but thank you so much for inviting me. It's an honor for me to present here. Thank you, Deepak sir, as well. Let me start today's session. Welcome everyone, and thank you for being here. Today I'll be presenting on vision language models in medical imaging. This is a fast-moving area of research that sits at the intersection of deep learning, computer vision, natural language processing, and clinical diagnostics. The goal is to explore how recent advances in AI can bridge visual medical data with clinical text to uh, build intelligent multimodal systems that can assist healthcare professionals. Uh, though I really saw like a very warm introduction about myself. This is just a short summary. I'm currently working as a machine learning engineer at Latent AI. I pursued my master's in computer science from Arizona State University, where I was honored with the Outstanding Research Award. And my research has spanned various topics Some major topics include medical image analysis, vision language models, and document classification. I've also shared my LinkedIn QR code. I'll be more than happy to connect with all of you. With that being said, let me start by highlighting just how rapidly AI is becoming the embedded solution in healthcare. A recent report shows that 2 in 3 physicians are now using some form of health AI, which marks a 78% increase from 2023. Now that's a dramatic surge and a strong signal that AI tools are moving from research labs to routine clinical practice. There are also powerful personal stories. So one headline that recently created a widespread attention was a man credited ChatGPT for helping diagnose a life-threatening disease. And then we also see some other news across the board, like AI is already reshaping care, what it means for doctors. So this shows that the conversation has now shifted. It's no longer about whether AI will play a crucial role in healthcare. It's all about how, when, and to what extent. And that brings up to today's topic, vision language models, a powerful class of AI models that basically play a key role in clinical text transformation. Let's trace the path that brought us here. It all started in 2012 with AlexNet. AlexNet used CNNs to dominate ImageNet, kicking off the deep learning era. By 2015, AlexNet introduced residual connections, allowing for very deep vision models. In 2017, the transformer architecture revolutionized NLP by enabling full attention-based modeling. And this gave rise to foundational models like BERT, GPT-2, and later GPT-3. In parallel, in the computer vision space, we had vision transformers being applied to image data. And then in 2021 came CLIP, one of the most breakthrough works in vision language modeling. CLIP used contrastive learning between images and natural language to learn a joint embedding space, which we will talk about later. And since then, we are seeing a lot of models come up like Blip, Flamingo, and MetaPalm, which have adapted these ideas for specialized domains like healthcare. Before diving into vision language models, which is the crux of today's talk, it's crucial to understand what are foundational models. By definition, a foundational model is a large pre-trained model trained on broad data at scale and designed to be adaptable to many downstream tasks. Unlike the traditional CNN models that are trained from scratch for each task, foundational models are pre-trained once and then fine-tuned or prompted for specific applications. Their scalability and generalization makes them especially useful in domains like medicine. This image right in the screen beautifully illustrates the power of foundational models, where on the left you see data being shown with various modalities, and it's being used for the model's training. And on the right side, you can see how the features it learns during the training process help it to leverage those features during adaptation or inference, where you can see a wide array of tasks from question answering to sentiment analysis to image captioning. So pretty much every or any vision language task that you can think of. So this is the power that these foundational models hold as compared to the CNNs. This table highlights the key differences, where CNNs are trained end-to-end for a single task, as I said, whereas foundational models, on the other hand, are multimodal and are pre-trained on enormous diverse data sets. And they support transfer learning, allowing for zero-shot or few-shot adaptation, which is a major shortcoming of CNNs. They don't generalize that well. And for example, let's say a foundational model just trained on radiographs and reports can also be fine-tuned to detect pneumonia or generate a structured report without the need for massive labeled datasets. Another shortcoming of CNNs is that they require a huge amount of labeled datasets to learn the right set of features. This Venn diagram shows the landscape of AI at the broadest level, where on the left, where we see the blue part, are vision-based foundational models, which only understand images. And on the right, the red part, are LLMs or language-based models. And the intersection of these two are VLMs, vision language models, which understand both these modalities, vision and language. Today's talk will be focusing on the models in the intersection of these two worlds, like clip, align, lava, and many more, which we will cover in the slides to follow. So this till now has set the tone for today's presentation. Now let's dive into vision language models. Vision language models are multimodal models that jointly learn from visual data and natural language to perform cross-modal understanding and generation tasks. This picture right in center of the screen again beautifully illustrates what a vision language model can do. For instance, on the left you can see a variety of tasks. Let's focus on the first one, object localization. As I said, vision language model understands both text and image as an input. So we can see the image, which has two cats, is being fed to the model, and it also has a text prompt. In this case, you have a question. The question says, "Is one cat behind another?" And then the vision language model, using its learned embeddings, tries to correlate the text in context of the image, and then generates a response accordingly, saying yes, one cat is behind the other cat, and then also generates some more data. And this was just one example. There are another variety of tasks which you can do, like zero-shot segmentation, zero-shot visual question answering. And the key thing to be highlighted here is the zero-shotness, that once a vision language model is being trained on significant corpora of data, it has the power to be generalizable. So unlike unimodal architectures like CNNs or LLMs, VLMs leverage joint or aligned embedding spaces to model complex interdependencies between two modalities, image and text. This pyramid here is a great way to understand the concepts behind VLM. Uh, First and foremost, the joint embedding space, where both image and text are mapped into a common latent space to enable alignment. And the way it does that is using contrastive learning. Contrastive learning plays a central role in its training, where models like CLIP learn to bring together the matching image text pairs and learn to push apart the mismatched image text pairs. So what's really happening is the model is trying to understand the correlation between the right image and its right text or the caption, and it's trying to disassociate the pairing between a wrong image and its caption. That way, it learns to understand image and text better. Thirdly, cross-modal attention is used in models like Flamingo or Blip to allow the model to focus on relevant image regions when reading a text, and vice versa. So, for instance, in the earlier slide, we saw it had an image as the input, and we were asking where is the cat in the image or something like that. So this is exactly where cross-modal attention comes into the picture, where with a text prompt, it tries to understand spatially where in the image is the cat. This is only possible because of cross-modal attention. And lastly, we have multimodal pre-training, where most VLMs rely on it to generalize well across tasks. That is the main reason why they are so well known for generalizability. Now, a great way to understand VLMs is by segregating it into the types of VLM tasks. And as we dive into each of these tasks, we'll cover some of the significant architectures in that domain. First and foremost is image text matching, which is used for retrieval and classification kind of tasks. Second is text to image generation, where we synthesize the realistic medical images from textual descriptions. This is useful for synthetic data generation. Third, we have report generation, where generating diagnostic reports directly from an image. And fourth is visual question answering. So answering structured or natural language questions based on an input image. And each of these are supported by various VLM architectures. Let us look at the first task, image text matching. In this task, the goal is to align visual features with textual content. It is commonly used for image text consistency checks or trying to associate both these modalities together. This model is trained using contrastive loss. As I said, contrastive loss is all about the motivation of contrastive loss is to associate the right pairs together and to disassociate the wrong pairs. Technically speaking, in an embedding in a latent space, the goal of the loss function is to minimize the distance between the right pairs. So you can see in this image, Let's take as an example the first and the second image of the dog is what a right pair because both of the images are a pair, positive. Whereas if you compare the central image with the bottom image, it is an incorrect pair because it's a dog and an owl. So from a model's learning point of view, the goal would be to minimize the distance between these two inputs in the latent space and maximize the distance between these two inputs. And that is how the model learns the concept of correlation. The idea here, or the main motivation of doing this, is generalizability. There have been several models that have used this concept, starting with CLIP, and then there have been some models that have been specifically developed for medical imaging, like Check0 and MedClip, which enable zero-shot disease classification based on the contrastive pre-training. So let us look at those architectures. Starting with CLIP. CLIP was a breakthrough work which came in 2021, which was one of the initial pioneering works to bond image and text together in one learning mechanism. So CLIP uses a transformer-based encoder, text encoder, and a VIT-based image encoder. So you have the image models, you have the images flowing through the image encoder, and you have the text flowing through the text encoders. And the on both of these are projected into a shared space, like you can see here, and they are aligned using cosine similarity. Cosine similarity is just one way of similarity. It's just a similarity metric. So you basically take the dot product and you try to correlate the right pairs together, and you try to increase the distance between the wrong pairs. What is the major benefit of this, though, is if you see point number 2 here, or point number 3 here, for zero-shot prediction. So after being trained with such image text pairs, both these encoders know exactly the correlation between the right pair, which helps them generalize. So let's look at the inference example here. In the inference, you just pass an image of a dog, which the model has never seen before. And then you also pass an array of different classes, plane, car, dog, and so on. And you then format it into a template, a photo of an object, and then you pass it to a text encoder. So essentially, the text encoder will have various options based on the number of classes. And using the same cosine similarity concept, image encoder and text encoder will go through a series of computations and then output the match which has the lowest or which has the highest cosine similarity, basically which are the closest in terms of latent embedding space. So in this case, it's a dog. So what CLIP model essentially means here is among all these classes, in terms of similarity, dog is probably the most similar with this input image. So this was the, as I said, one of the first pioneering works. And then there were several variants which utilize the same concept but for various applications. Like here you can see a similar matrix, a similar learning mechanism was introduced for medical data, where you had from the text reports, they first basically found out the major classes like lung lesion, lung opacity, and then built labels around it. And they sampled a batch of images and a corresponding batch of reports from which they generated these classes. So it is pretty much the same layout what we had in the last slide. And then again, a semantic matching loss with a cosine similarity loss helped them basically associate a chest X-ray image with its appropriate label. Another similar work in this domain was Check0. Check0 takes this one step further and evaluates zero-shot classification directly by comparing chest X-rays against natural language prompts. So instead of going through the step of finding the right classes and going through some text pre-processing, what they did is they directly used a CLIP pre-trained transformer and then directly started contrastive learning with it. The result was an even better zero-shot pathology classification, where you have just prompts where you have no pathology and pathology being passed through the text transformer, and the image is being passed through a vision transformer, and then similarly, cosine similarity matching gives you the higher similarity option. So in this case, the model thinks this is a image of no like a negative prompt. We can see the similarity is being higher on the left side. So this was our task one, and the reason why I call it task one is because it really lays the foundation for the several coming tasks. Right, the first task, as I said, was image text matching. So learning to associate image and text modalities in one in joint feature embedding space is crucial for the other task to function. Let's move on to the next task. Task two is one step of complexity above it, where you have to generate an image from a medical description. Or speaking purely in a computer vision sense, you pass it a natural language prompt and it learns to generate images. This is typically done using a latent diffusion model. The text prompt is first encoded into a latent representation using a transformer, and then a diffusion reconstructs it as an image. On the right side, what you can see here is again another groundbreaking work, which is called DALI. The way how it functions is the shaded portion or kind of transfusion portion here is its training mechanism, where in the training process it uses a discrete variation autoencoder to just learn how to deconstruct images. So you have an input image, it learns those input image into a token space, and then just typically have a discrete variation autoencoder functions, and then learns to reconstruct it. And parallelly during training, it also saves the important tokens in an image into a memory bank. And then during inference is what is shown in the upper part of the image. All you need during inference is a text prompt. And they use a pre-trained transformer here, which basically learns or knows already how to convert text into meaningful tokens. So if you see here, what already being happened is the text is already processed into a latent space, and then you just pass those embeddings directly to the discrete variation autoencoder, but just the decoder part, because the latent embeddings have already been computed. So now when you pass them to the decoder already has learned how to decode an image from a latent distribution. So even though it was trained on let's say this image, if you pass it armchair in the shape of an avocado, it will most likely create 10,000 other images which are exactly matching this description, but which are not exactly the same as this image. This is the beauty of latent space, that the model learns to not just stick to one image, but to create several variations which also hold true for the given text prompt. And if you think of how this can help in medical context, right, for synthetic data generation, or for synthesizing images for rare diseases, or creating training datasets where real examples of scars, the applications are plenty. There was another work, before diving into the medical works, another work which you should focus on is Unclip, which is the successor of the earlier model with DALI-2. It's also called as DALI-2. Unclip is the image generation component of DALI-2, where instead of generating images directly from text, it first converts it into a clip text embedding. Then Unclip, which is a diffusion-based decoder, generates an image that matches the semantics of that embedding. Note that the prior which is mentioned here is basically a pre-trained decoder which learns how to map a latent space to generate an image. And thus, in essence, why it is called Unclip is because it works by reversing clip, where clip maps images and text into the same space, and Unclip takes that embedding and decodes it back into the photorealistic image space. So this is text to image. And now moving on to some works which adapted this technology or this concept for medical domain. Rowan Jen was one of the first works, which is the domain-specific text-to-image model. It is designed to generate chest essays from radiology reports. It adapts diffusion-based generation techniques similar to what we saw in DALI-2, but it is trained specifically on medical image text pairs. The model takes a textual input such as clinical finding or impression and generates a synthetic X-ray image visually. On the right, you can see the text that was passed to it, like for instance, small right-sided pleural effusion. And what's remarkable is that it comes up with a synthetic image which exactly matches the description. And this basically helps to generate synthetic images, which can have a variety of applications, like I said, including creating more training data or making a specialist model which focuses on a particular class of disease for which the real images are very scarce. And then there was another work called MINIM, which stands for Medical Image Generation via Natural Language Diffusion Models. It's a text to image generation model similar to the previous works, and it is designed specifically for radiology. It uses guided diffusion to synthesize text essays conditioned on detailed radiology report text. Unlike general models, MINIM is trained on paired medical image test reports. So quite similar to what we saw in the earlier slides, but in the training set or during the training phase, they adapted it to a lot of modalities. And even the text prompt was conditioned in a way where this was the format, where you have a modality and their description. So they had a much more robust and comprehensive training regime, which allowed them to create a generalizable model which can generate any of these modalities. So on the right, you can see these are all synthetically generated images, but from just one model, which is which goes one step ahead of the previous models we saw. Uh, Now moving on to the task 3, which is medical report generation. So report generation or MRG involves producing a structured radiology report from an input scan. This is a challenging task because the model must detect abnormalities and translate findings into clinically accurate language. Cross-modal attention is the key here. So a typical framework of MRG is as shown on the screen, where you have an input image which is passed through some feature extraction process, and ultimately there is a text generation component which knows how to decode it into decode the learned features into a meaningful text representation. But the key thing to note here is that it requires strong cross attention and alignment, because exactly delineating the abnormality present in the image just from one single X-ray image is a very tough task, and it requires some really strong training guardrails, which we will see in the following slides. This is one slide which I saw from one of the survey papers, and it is really a nice way of understanding how medical report generation operates and how we can segregate it into various ways. There are 4 major ways how MRG is done, starting with autoregressive generation, the part A, where you have an text image where you have an input image which is passed through some encoding process where you get the visual features, and then it is passed through a decoder in an autoregressive manner where it just computes or translates it into text in an autoregressive way. I would say this is the vanilla approach. Then in part B, we have hierarchical generation, where the left part of the process stays as the similar, but once it is passed through a sentence decoder, there are various hierarchies of word decoders, where the top level might just say whether the image is normal or abnormal, and the layer below it would be focusing on basically delineating what exactly is the abnormality, if abnormality is present. And the layer below it would then focus on delineating exactly which part of the image has that anomaly or something like that. So you can see the output is quite the same, but the way the output is computed is through hierarchies. And then we have template-based generation, where again the left part says as much the similar, and the right side of it is using a template database, where once you have learned the visual features and then you're passing it through sentence decoder, it learns to decode it into a particular template so that the template stays consistent. This is useful when you are generating reports for a lot of images and you want consistency. And lastly, we have LLM-based generation. This is by far the most used approach for medical report generation, because right now we already have LLMs which know quite well about medical text. Like we have Llama and we have other powerful LLMs. So in this, once you extract visual features from the image, you just pass it to LLM, and then with some prompt, you prompt it to basically generate a detailed medical report. You probably give it some background context, but then LLM is already well trained enough to generate a significantly thorough report for the input text image. So these are the four major ways of MRG. And this is one work which uses the part A, the autoregressive one. Like you can see, the medical image is being passed to an image encoder, and then a sentence decoder, and then you have a word decoder which basically generates output tokens serially, and then you have another added component of reinforcement learning. So reinforcement learning here is basically the way they used it in this paper was they use a reinforcement learning method to basically reward the correct reports or the right generations, and to disregard the generation which were hallucinated. So this is another good way of trying to achieve accuracy during training using reinforcement learning. Now coming to a significant work, MedPalm-M, which is right now breaking and creating waves at the internet. MedPalm is by far the most generalist model designed for medical domain. It is a generalist vision language model. It processes multiple modalities, including medical images, clinical text, structured data, using just one unified architecture. The model uses a frozen vision encoder to extract image features and a text encoder decoder to process and generate language. The core concept remains the same, but they have just expanded it to a lot of modalities and a lot of different tasks, which makes it a generalist model. So that's the difference between a generalist and specialist. A specialist model is a model which is trained for a particular type of task. For instance, it can be pathology or report generation or visual question answering only for genomic data sets. But a specialist model is a model which uh, understands various modalities and is also able to do various tasks. So in this case, you can see on the left we have various modalities which it supports, and on the right you have the different tasks which it can do. One thing to note here is that the major reason why they were able to achieve this is because of a comprehensive and a thorough training routine, which was probably computationally expensive. Uh, Another thing here is that they have specifically mentioned in the paper that this is a prototype, meaning that they plan to make this work more robust. But you can see in the next slide why they call it a prototype. So this slide shows examples where text SQLs are input, being passed as an input, and the model is being asked to answer some questions based on the findings it sees in the image. The important thing to note here is that we are using prompt tuning, where you can see the instructions. You first give it some context. You are helpful radiology assistant, and you first give it an input image, which is a normal X-ray image, where you ask it, is it a normal X-ray image? And that input probably wasn't a normal image, so you also gave it the answer. No, there's some sort of pleural fluid. And then you give it the actual image which you want it to answer. And based on this information in its context, it answers the following question. The thing the highlighted here in blue is the correctness of its prediction, where it was able to predict that a cavity lesion in the right upper lobe, and associated pleural thickening and so on. The thing highlighted in red is what it missed out on, or probably what it hallucinated. So this slide exactly shows the state of the art where we are in medical multi-image, multimodal processing, where you speak of a generalist model, it is probably not there yet to answer every detail, every minute detail clearly for all the modalities. For some modalities, it might really answer well, but like you said, like you see here, for some imaging modalities, it's not quite there. It does some hallucination or misses out on some of the key important parts. And with that being said, let's move on the last task, which is the visual question answering. Visual question answering takes an input image and a natural language question. For example, the question can be something like, is there a fracture in the left leg? And you just pass the bone X-ray of the left leg. And then you expect the model to return an answer like yes or no fracture seen. This task requires both image understanding and text reasoning. because now you are not just talking about localization or some sort of classification, but you are also asking the model to reason. If the model says yes, it sees the fracture, you expect it to also give you a description saying why it sees that. So it is especially this task is especially useful for applications like AI assisted diagnostics, where you have an intelligent model and you just want it to see a corpus of input images and then generate some reports or generate some answers based on those images. Fleming was is one of the works which was pioneer in VQA, but it was not on medical data. It was on general computation data. And the way it operates here is it uses the perceiver module that receives vision embeddings and fuses them with the language prompts through cross attention layers. So this was one of the first works which actually embeds the input tokens directly into the cross attention layers. So you can see there are two prompts displayed here. On the left, there is an image of a dog, and the way it functions is quite similar to that of a prompt tuning, right? So on the left, you have an image of a dog, which is passed through a pre-trained vision encoder, and then this perceiver resampler function directly embeds that into the cross attention layers. But with the input text, you also give it a description saying for this image, this is a very cute dog. And the model learns to associate this image with this dog. And this is all in the inference though. And parallelly, you also added another input image and pass it in the same way. But you want the model to answer this image. So you just say this is and leave the rest. So in the inference, what is happening is the model associates this image and its text that it is a very cute dog. And this is probably what a cute dog looks like. Similarly, it uses its learned embeddings to then info for this for the cat image, and then it generates a description saying a very serious cat. So there are two things happening here. Firstly, you are understanding the model is understanding the image and text quite well using the cross attention layers, and secondly, all of this is happening during inference, which means that this wasn't a part of pre-training. And one major reason why it is able to do so well is because it uses pre-trained vision encoders and a pre-trained LLM model, which both of these models are thorough enough with their own modalities, so they understand how to encode their modalities in embedding space very well. So these works are just leveraging the groundbreaking works of the foundational models. So we have vision encoders, which is probably a vision transformer which was trained on enormous corpus of data, and Flamingo just uses that for their application. There was another model, LavaMed, which is a medical variant of the model Lava, which is basically Lava with domain-specific adaptation to medical language. The key input, the thing to understand here is the Lava is again similar vision, visual question answering model, where you give it a input image and some caption, and then give it a prompt. It then learns how to generate basically a caption for the image. The groundbreaking thing with LavaMed, which they claimed, is that as you can see in the the upper image, they claim that they were able to generate LavaMed in just one day. And how they did this is just because of the power which these foundational models have. Like I said, with just one epoch on 600K samples on the medical concept alignment training, and just 3 epochs on 60K samples for the instruction tuning. So these were the 2 stages of the training process. But the reason why just one epoch on and just 3 epochs were enough is because the models which they use as backbones are pre-trained models. This is exactly the generalizability which I was talking about in the first few slides. The major reason why VLMs are such a huge success is because they are generalizable. They have been trained already on enormous corpus of data. So even in this example right here, Lava didn't start from scratch. They used pre-trained models which already knew vision and language space very well. All they had to do was just fine-tune it for medical context. So just one epoch, which took 7 hours, was enough, and just 3 epochs for the instruction tuning was also enough. And then they had LavaMed, which is the Lava, but it understands the medical context well. And you can see in the image here, they claim that it is much more robust than a normal Lava or a normal GPT-4. So now having looked at various tasks and various architectures, where each architecture was doing some different tasks, let's summarize the timeline on how VLMs have evolved in just a few years. It all started in 2021 with Clip, so just 4 years back, where Clip demonstrated a general purpose vision text alignment using contrast learning over 400 million of image text pairs. And there was another model, Convert, which adapted this strategy for radiology by training the same clip on radiology image text pairs. Then the following year after that, 2022, we had Gloria, which introduced a local global alignment strategy for better fine-grained medical imaging matching, which was again along the similar lines, but the core concept behind it was getting slightly more robust, and the generalizability was also being improved. Then we had MedClip, which we saw, which was basically a clip adapted to incorporating domain-specific encoders like BioBird. So in Clip, we have a natural language model which doesn't understand medical context, but in MedClip, they used BioBird as a text encoder, which basically helped them generalize well for medical data. Then the year after that, we had models like Blip2, which introduced a two-stage architecture with a frozen vision encoder and language model. And we also had Mini GPT and Lava, which were basically conditioned to support image text reasoning quite well. So even in 2023, GPT unlocked its image-based reasoning. So you could just pass it an image and ask it some question, and it would answer you based on that image. So around 2023 was a time when vision language reasoning was really being explored. And then finally, we had last year, we had MedPalm and Check0. So MedPalm was basically, as I said, one of the first generalized works to integrate text, image, and structured data to deliver a generalizable performance across 5 medical domains. So there were some caveats with that work, which they themselves addressed in the paper. Like I said, sometimes the model was hallucinating, and sometimes it missed out on some features. But that was probably because they were shooting for a very ambitious task of making it generalizable for 5 different modalities. So this is the landscape of how VLMs have evolved over the last few years. Another important thing to note here is the Gartner AI Hype Cycle. The Gartner Hype Cycle, for those of you who don't know, is a framework that tracks the maturity and adoption of emerging technologies. So it maps them through 5 phases, from early innovation to real-world productivity. Let us look at the left plot, which was for the year 2020. In 2020, the generative AI was just entering the cycle at the innovation trigger phase. You can see generative AI being marked at the initial, like at the first half of the curve. So it was still on the curve, but towards the upward scale. So it was a signal of an early promise, but limited adoption. And just 4 years later, by 2024, it has rapidly ascended to the peak of inflated expectations, showing just how central it has become in the AI conversation. Notably, Gartner also introduced foundational models last year, because for the first time they introduced this node called foundational models, because this term didn't exist before 2022 or 2023. So you can see, just from analyzing these 2 charts, you can see how the landscape of AI has shifted and how the hopes in generative AI have increased for it to make the generalizable AI notion come to fruition in a medical context as well. So just summarizing why vision language models really matter in medical imaging. VLMs offer multimodal reasoning, which is crucial in healthcare. Clinicians, even real-world clinicians, don't make decisions based on just images or just the text. They integrate symptoms, lab results, and prior reports. VLMs can now do the same by aligning textual and visual information. VLMs also support diverse tasks in a single framework, from diagnosis to documentation to image generation. And because they are built on foundational models, they generalize really well to new tasks with minimal supervision, which was a major caveat before foundational models came. And this flexibility makes them a natural fit for the complexity of healthcare scenario. And let us brief over some advantages. First, they make use of existing radiology reports as weak supervision, reducing the need for manual annotations. Secondly, they enable few-shot learning, which is especially valuable for the rare conditions where labeled data is quite limited. Thirdly, they improve interpretability by producing human-readable explanations. Fourth, they support content-based retrieval. For example, finding cases similar to a new patient. And finally, they also support multitask flows, where we saw something like MedPalm, which was capable of doing classification, generation, and even retrieval, all with just one model, and that too for various modalities. Despite their potential and the success which they have shown, VLMs also face some challenges. Let us brief over them. Firstly, the data bias. Data bias is a huge concern with VLMs because most of the public data sets which they have been trained on, for instance, Mimic CXR, come from US hospitals, and they may not generalize that well globally. Second, hallucination is a risk. Models sometimes generate plausible but incorrect text, and even sometimes miss out on some important features. Uh, Hallucination in general is a risk with LLMs as well, but when you think of the medical context, the stakes are even higher. You cannot afford to have some hallucinations for any image, which just hampers its applicability in the medical domain. Regulatory concerns are also another major caveat. And even training and deploying these models requires significant computational resources, which is another reason why you see most of the VLMs and LLMs out there only come from 3 to 4 companies, because developing them is a huge resource constraint problem. And finally, from a explainability point of view, uh, most VLMs lack the transparent mechanisms to justify their predictions. Uh, though explainability is being explored, I would say, in VLMs, where the upcoming recent VLMs do explain their prediction or the reasoning to some degree, but it is not quite there yet to confidently explain the intricate reasonings behind, especially if you talk about medical context. If you pass it and input a radiology image, a chest X-ray, or a CT scan, it is not quite confident, or it is not quite clear what makes them predict a particular token, or what makes them classify the image as a particular class. So explainability is another portion which needs to be explored. Looking ahead, there are several research directions which stand out. First, we expect to see more large with generalizable multimodal models that combine vision, language, and structured data for complex diagnostic reasoning. Second, privacy preserving methods like federated learning will allow hospitals to collaborate without sharing their raw data. So that is another reason why VLMs haven't been scaled that well, because the privacy aspect isn't well explored. If VLMs somehow support federated learning or other privacy preserving methods, then we could see VLMs being developed more in a scalable way. And thirdly, these models will expand beyond radiology to other domains like ophthalmology, pathology, dermatology, and even genomics. Right now, we only see most of the VLMs in medical domain being trained on radiology tasks. They understand CT and X-ray quite well, even MRI, but the other modalities are not quite well established yet. So these are the 3 major future directions. And with that being said, thank you so much for being a great audience. I hope this talk was helpful. If you have any questions, I would be more than happy to address them at this point. Thank you so much.
Participants, if you have any query, you may ask. Participants, you may ask questions regarding the session if you have. Okay, otherwise we will move with the next session.
Yeah. So please check the chat box if there are
Okay.
any queries.
I think there is no query for this session. Anyway, thank you, Amol, for your insightful session. Definitely, I hope participants have enjoyed it, and also in future we may take your insights in these research fields. Okay, so
Thank you so
thank you
much for
for your
inviting me.
time.
Sure.
So, Amol, you
Okay.
may leave.
Yeah.
We may leave. We may go with the next session. Thank you so much. So participants, be with us. Dr. Deepak and Nayak will be joining us soon.